Hey everyone, so we are here with worksheet number 16, and the semester is winding down, which is really exciting. So, what a way to start a video. Okay, so number one says that we wanted to find this relationship. I think this is called a tilde, or like, I call it an enye. I don't know, whatever. We wanted to find this relationship on R. Yeah, it is tilde. X tilde y if and only if x minus y is an integer. So x minus y is in the set of integers. That means that, like, if x and y are both integers, then we're going to be good to go. But we say here that x and y could be any real numbers. And it's kind of like, when I first look at this, I'm just thinking about, like, the possible ways that x minus y could be an integer. And, like, the most obvious way is if they're both integers. An integer minus an integer is always going to be an integer. But, like, let's say y equals 2.3. Then we just need x to be some number that ends with 0.3. It could be, like, x equals z.3, which could be, like, 5.3 or 7.3 or 1140.3, because then if you subtract 2.3, you're going to get an integer, because the 0.3s will cancel out. So that's just, like, my initial thought when I look at this before even, like, seeing what the questions ask me. Okie doke. So part A says show that tilde is an equivalence relation. So we learned about equivalence relations last time, and there are three criteria. Relation. Three criteria. We have to show that it's reflexive, meaning it has fast reflexes. Symmetric. And transitive. Okay, so reflexive means x tilde x is true. Or x tilde x is true. That's reflexive. And we could show that by saying x tilde x means x minus x is an integer, which means 0 is an integer, which is true. Easy enough. Similarly for symmetric, just going to say sim, kind of running through this part because we already did equivalence. So for symmetry, we have to show that x tilde y implies y tilde x, that if that first criteria is met, this part, then the opposite relationship is true. And that means that if x minus y is an integer, that implies that y minus x is an integer. And this is also kind of like self-evident because of what I said at the beginning, that if they're both integers, then by flipping them around, you're still going to have an integer. And if, like, one of the numbers is not an integer and it ends with, like, a 0.3, then the other one is going to have to also end in that 0.3. So if you flip the order in the difference in the subtraction problem, then you're still going to get an integer. But a more rigorous proof would be that x minus y, let's call it a, where a is in z. We're allowed to do this. If we say x minus y is an integer, we could also say x minus y is some arbitrary a, where a is an integer. This and this is saying the same thing. So then y minus x equals negative x minus y, which equals negative a. And that's also in z. So therefore we have symmetry. And yeah, hopefully that's clear. And then the last step is transitive. And here, this part involves a little more math. Transitive. So here we're saying x tilde y and y tilde z implies x tilde z. So let's use the same kind of methodology as we did last time. X minus y equals a, and let's say a and b are integers, just putting that off to the side, and we have y minus z equals b, then x minus z. You could do algebra here. You could say x equals a plus y from this equation, and z is equal to, add the z minus the b, y minus b. So x minus z equals a plus y minus b, which equals a plus b, which is an integer, because a and b are both integers. Bam! Yes. Another way you could do this is by seeing that, well, it's actually really the same, but you could just see that x minus y minus z equals, oh, that equals x plus z, doesn't it? We're taking minus y. Oh no, you have to add these two. That's what you gotta do. So you could just add these two, and you end up with x minus z. So you could see that if that's an integer and that's an integer and you add them together, you end up with an integer that's also the same as x minus z. And yeah, that seems kind of redundant what I just did, but whatever. The point is, you could either solve for x and z, or you could recognize that by adding them, the y's cancel out. All right. Now, part B says, prove that the equivalence class 0 of 0 in R is the set Z. Okay, I think this is really simple. So basically, it wants the equivalence class of 0. So that is all the, I think we use curly brackets for this. It's all the x in R, because we know that x and y are contained in R. We have that over here. So we want to start with all the x in R given that x tilde 0. Yeah, that's basically what we want. And whenever we're doing an equivalence class, it's important to recognize that if we're using the structure of x tilde y, which is most of our cases, then whatever we're finding the equivalence class to is replacing our y, not our x. So that's like it's really the only like thing that I see people get tripped up on in these types of equivalence class problems, is what the 0 is replacing. So remember, x tilde 0, x tilde y says that x minus y is an integer, so x tilde 0 is saying x minus 0 is an integer. And you're going to see this problem is going to solve itself very quickly. So that's the same as x in R, given that x minus 0 equals a for some a and z. That's our way of calling it an integer. So, which is equal to x in R, where x equals a for some a and z. And once we do this, we might as well just erase that and just say x is in z, right? Because we're saying x equals a where a is in z. We might as well just say x is in z. So that kind of gives us our solution. And our goal was to prove that it is the set of z. So this is basically now what we've gotten to, is we're saying that the equivalence class of 0 is all the real numbers x such that x is an integer. And since integers are contained, since we have this relationship that the integers are contained within the real numbers, we end up with the set of integers. All right. So now part C. We have to prove, it's asking us to prove that the equivalence class of p over q is, it's a little confusing the way it's written. In R, okay, I'm just going to say, when it says like prove that the equivalence class of something belongs to some subset or some set, just find the equivalence class organically and then deal with that proof part at the end. So basically what I'm telling you, the advice that I'm giving for these types of problems, is ignore the whole prove thing and just find the equivalence class of p over q. So let's just talk about the equivalence class. So here we're going to start with x and r again. We're always going to be starting with x in whatever universe that it belongs to. And here we said that x and y are contained in the real numbers. So that's what we're starting with. And now we're saying the relationship x minus p over q. I'm skipping a step. You could say x tilde p over q here. And then that's equal to x minus p over q equals a for some integer a. And now we're going to try solving for x. So this is not very challenging either. X in R, x equals a plus p over q. And this is actually really similar to something that I sort of mentioned in passing at the beginning, that if y equals something like 2.3, x equals integer plus 0.3. That's basically what this is telling us right here. We're saying that a is an integer, that's our integer, and that is our like remainder. That's our like ugly remainder, like our 0.3. So now the question tells us prove that it's a subset of the rationals. So now all you have to do is show that a plus p over q is always rational. And we know that a is an integer, and we know that p over q is rational. So one way of showing this would be to say, you could say that a plus p over q is equal to aq plus p over q. I just multiplied the a by q over q, doing nothing to it, but so that I could express it like this. And a q plus p and q, both of those terms are contained in z. And when we have an integer over an integer, we know that that's rational. So that would be a way of demonstrating that this set over here is always going to be rational. It's contained within the rational numbers. So I didn't write out the proof kind of exactly how you would want to write it out on an exam, but hopefully this is still helpful. And then finally for part D, we need to find the equivalence class of the square root of 2. And if you've been paying attention so far, hopefully this is like intuitive at this point. But basically it's a set of x in the reals such that x tilde, this time I'm going to do all the steps. I'm going to make that 2 look a little bit less like a z. And remember, x tilde square root of 2 means that x minus the square root of 2 is an integer. And we're going to say that right now. X is a real such that, but we want a subset of the real numbers. X can't be just anything. It has to follow this specific condition, which is that x minus the square root of 2 equals a for some integer a. And that is equal to, we want to say something about x. We have this thing where x is a real number, but we have a condition on x, and that's our condition. So now we want to use this condition. We want to have this condition in terms of x. That's why I'm doing the algebra. So I'll show you this. X equals a plus the square root of 2. And yeah, I think we all saw this coming. This is just like our a plus p over q, Here we have a plus the square root of 2. So it's basically every number that is an integer plus the square root of 2. Cool. That's our equivalence class right there. Bam. All right. Now we are on to question numero dos. Let's switch to pink. To find a relation on R given by x tilde y, and I'll just put an R up here so that we know that that's the universe we're dealing with, if and only if x minus y is rational. Show that tilde is an equivalence relation. Okay, I almost don't even want to do that. Yeah, so Professor Carbone said that the equivalence relation part is similar to Q1. I could try to work through it. I haven't actually worked through this, so I'd be doing it live. And yeah, let's give it a shot. Let's test my abilities here in front of you guys, and we'll see how we do. So equivalence relation again is, so let's start with reflexive, which means x tilde x, which means x minus x equals 0, which is rational. Good. Now symmetric, x tilde y implies y tilde x, and so that means that x minus y equals p over q. Oh, this is easy enough, which is rational. So y minus x equals negative p over q, which is also rational. And that's the same idea as like, if x minus y is a, then y minus x is negative a. So here we have the same type of relationship, and we know that if p over q is rational, that negative p over q is also rational. To be rational, you have to have a fraction of two integers where the denominator is not 0. That's all it takes for a number to be rational. So that is satisfied here. And now transitive, this should be the hard one. And transitive will say that, I'm skipping a step, I'm not doing the tildes here, but it says that if x minus y equals p over q and y minus z equals, say like r over s, yeah, let's say r over s, then x minus z equals, well, it equals, we already know from last time that it equals x minus y plus y minus z, which is equal to p over q plus r over s. And we could like multiply these to make it into one fraction. I don't know why I put parentheses around them, but yeah, we could multiply this times s over s and this one times q over q, so that we could get this clear picture of ps plus rq over qs, which is rational. Okay, so that's basically it. And the reason I know this is rational is because ps, rq, all of these variables are integers. So when you add them together or multiply them like the denominator, it's going to stay integers. Cool. Okay, now let's talk about some equivalence classes. I do feel like this problem is very similar to problem 1. So I feel weird like doing all this work. But yeah, so the equivalence class of 0 is going to be, so here we want x and r again. Remember we said that r is the universe that we're working with right there. And this time it's the set of all the real numbers x such that it has to satisfy this formula of x minus 0 equals p over q. And this is a bit of shorthand. You could say where p and q are both integers and q is non-zero, or you could just say like p and q is rational. I think this notation is okay. And this is equal to the statement that x in R such that x is rational. I'm able to cut out all this garbage because I'm basically saying that x, by saying x equals p over q, like if we get rid of this 0 here, that's not really necessary. So by saying x equals p over q, that's rational, I'm basically just saying that x is rational. So I could kind of just skip to this and cha-ching. So our set is all of q. It's x in R such that x is also in q. And since, again, q is a subset of R, this is really similar to, if we go back, this example right here, where we get x is, that basically the equivalence class of 0 here is all the integers, and here the equivalence class is all the rational numbers. And now we have the square root of 2. And, actually I'm not going to do the square root of 2 because they ask one that's just a generic R, and I'd rather do that. I think that's a little more instructive. So what's the equivalence class of some generic real number R? And that's contained in the reals. It could be any real number. And this will cover the square root of 2. So if you're not sure about the square root of 2 example, it's going to follow the same exact format as this one. Just saying R is a little more general than the square root of 2, so it'll cover every example, essentially. So here, we're going to just follow the same guideline. X in the reals given x tilde R, which means x in the reals given x minus R equals p over q, which is in q. I hope this notation's correct. I'm going to ask Professor Carbone if this is allowed. It is a bit of shorthand. And remember, we want this in terms of x, because we're talking about a set of x's. X in R given x equals p over q plus R. So this is our answer. And the condition is that p over q is rational. So if we just want some generic R, we have to be able to add a rational number to that R, and that's our set. So if our rational number is the square root of 2, then, not our rational, if our real number R is the square root of 2, then our answer is just going to be x equals the square root of 2 plus some rational number. And the reason is because the tilde relationship, again, is x minus y is in q. So if we wanted to say that x minus the square root of 2 is rational, that means that x needs to be rational plus the square root of 2. Because then when you subtract the square root of 2, that's going to cancel out, that's going to cancel out, and you'll be left with a rational. So hopefully that clarifies everything. And yeah, the partition kind of follows that same form. The partition of R is the partition of all these R's like we just did. And that's the same as saying R in R, and we're just kind of repeating the set that we just came up with. X equals R plus P over Q. And yeah, I think that's a good enough answer. And you could also add that P over Q is rational and R is real. Oh, we already said that R is real, so you don't have to repeat that. Okay, cool. And last but not least, we will move on to problem 3. And for those of you clamoring for the color, oh, we already did yellow, never mind. For those of you clamoring for the color blue, now's your moment to shine. This is your lucky moment. Okay, so problem 3 says let S, I don't know, it probably comes across that this material like doesn't excite me as much as some of the stuff we've learned in the past. Yeah, it is what it is. we'll get to some cool stuff soon. So let S be the set of all quadratic polynomials with real roots. This is what's written in the problem. That was brutal. Let's redo that. S equals. Now, some of you guys in class had a bit of trouble understanding this one, so I'm going to talk for a minute about this. Plus bx plus c given a, b, and c are real and b squared minus 4ac is greater than or equal to 0. This is called the discriminant. Okay. So, and then, okay, let's talk about the relation on S. Is f tilde g if and only if f and g have same zeros. Wicked. Okay. So basically we have this set S, and it's not a set of numbers like we are used to. Like z is a set of numbers. It's like -5, -4, -3. It goes to infinity and it goes down to -infinity. It's all the integers, right? So this set, we actually have a set of quadratic functions. So the set might include like 4x squared plus 6x plus 10, and it might have like 10x squared plus x plus 19, ... And it could have minuses in there. It doesn't all have to be positive. It just has to have real roots. It has to have 2 real roots. So that's kind of our only restriction there. Okay, so that's what S contains. It contains all of these functions of x. So f tilde g means that f and g have the same zeros. It doesn't mean that they're necessarily the same function. It just means that if you find the roots of x where it crosses the x axis, if you were to plot them, like yeah, all of these functions could be plotted on the xy plane, and wherever they cross the x-axis, that's their zeros. So f tilde g, these two functions have this equivalence relation only if they cross the x-axis at the same point. That's what we're talking about here. And we're told that it's an equivalence relation on S. So we don't have to prove that. Remember, we have those 3 criteria for proving that something is an equivalence relation, but we're already given that, basically. And now the question that we're asked is, we want to know what is the equivalence class of x squared minus 1. What is that? Big question marks. I'm not sure. So remember, to be equivalent to this function, let's call this one g of x. For f tilde g, they have to have the same zeros. Well, the first question maybe we should ask is, what are the zeros of this function? X squared minus 1 equals 0, so x squared equals 1. So x equals 1 or minus 1. So the zeros are 1 and minus 1. This graph looks like that, where that's 1 and that's minus 1. And this is minus 1, because that's our y-intercept. Anyway, so we need to find all the functions that cross the x-axis, all these quadratic functions that cross the x-axis at those points. And I'm going to use white here. So maybe we'll have some that are like that. You might have some upside down ones. And we need some way to represent all of them. And yeah, that's not so simple to think about. But basically, yeah, I'm not sure if there's a better way of doing this than just like thinking about it for a little while and trying to figure out what's a way that we could represent them. So all of them have to have these roots of 1 and -1. So that means that all of them have to have this term in it. Yeah, I guess the way you could think about it is like, how would we flip this parabola upside down? How would we flip x squared minus 1 upside down? The way we would do it is by multiplying it by -1. So contained in our equivalence set, let's just write down some notes. Set should be, the way we flip it upside down is by multiplying it all by -1. Should be negative x squared minus 1. And how do we, the way we kind of stretch our parabola, the way we would stretch it out is, or scaling it, is by multiplying it by something. So we could flatten it out by multiplying it by something that's less than 1. So we could like multiply it by 0.5 times x squared minus 1, or we could stretch it and do like 5 times x squared minus 1. And if you have like if you go on one of those like softwares where you could do a lot of plots, you could see this, where if you keep the x squared minus 1 constant and you just multiply it by different coefficients, you're gonna get the same zeros every time. Like even here, if we set this to 0, we're still gonna be getting that x equals plus or minus 1, because we could divide out the 0.5 and like cancel it out basically. So yeah. So ultimately the solution is that x squared minus 1, the equivalence class, is the set of all a times x squared minus 1 for given that a is a real number. And that's kind of what we've been describing. We were saying that a could be negative, it could be a decimal, it could be some integer like these, and all of those are possible solutions. The only restriction on a is that it's real. It can't be like I. It can't be the square root of -1. But yeah, I guess that's really more of an explanation of the answer than a way of figuring it out. It's kind of hard to say how would I go about figuring it out. I guess you just have to think of it. You just like, maybe if you just are able to imagine or plot out some of these potential solutions, you might be able to figure out the pattern that, yeah, I don't know, maybe some of you guys could tell me if you think of a way of coming about this answer. Anyway, I hope you guys have a good night, and I'll see you tomorrow in class, and yeah, be well.